welcome Professor Andrea Milani, who will talk about space missions for minor body science. And let me tell you that in this case, if you want to ask questions during the talk, you're very welcome to do it. So you just fire away during the talk. Okay?
Thank you very much. I think I've been in my career to more than 100 Congress school meetings, but nevertheless, I never gave a talk like this. So it's very experimental, and you will see. So the subject is the space mission for minor body sciences and how to take part in them. This is the point. So I will begin with self-presentation, a number of very personal remarks, and then I will illustrate with a number of case studies. So let's begin with Okay, so I will begin with presenting myself and telling you a small chunk of my personal history. You know, the problem is that an old person like me has a lot of memories, and it's a delicate thing to select which ones to use, because they have to be useful not for me, but for you. But on the other hand, you also have to learn how to use my memories. The intent is not to teach you to do as I did. This would be wrong. I mean, there is no progress. But you have to learn lessons to apply in innovative ways in your times. In the early 60s, I was a teenager, and I think it is difficult for the youngster of today to understand what was the spirit at that time. At the times of Gagarin and Glenn, of the Apollo missions, of the beginning of solar system exploration, I was a young enthusiast, including of human space flight, and also like computers, although at that time there was no way to touch a computer, not even with the tip of your finger, but still I did strange things like learning how to program in Fortran when I was 16. Let's make a big jump of about 12 years and go to 1976. I was age 28. I was already at a good point in my academic career, already at the tenure position at the University of Pisa as assistant of mathematical analysis. However, my impression was that my research career was going nowhere. I was not satisfied, not with my career, but with my research. Then, following the advice of Anna Nobili and Paolo Farinella, I attended a lecture of Giuseppe Colombo at Scuola Normale Superiore. Colombo was not lecturing in any ordinary sense. He was going to America about once a month. And he would arrive at the airport in Pisa, and in the car from which we are bringing you to the place where you're supposed to lecture, he started opening his bag, his very small travel bag, and showing us documents, which in most cases were marked confidential, containing secret, not yet published results from NASA observation and space missions. And then he was soliciting, actually challenging us to study the interaction of abstract celestial mechanics, which we were at that time studying, with solar system dynamics and even space flight. Now, the challenge of Beppe Colombo proposed research is not just knowing mathematics, but finding ways to apply it to the problems arising from the exploration of space, of the solar system, and even to the technological problems of space travel. Indeed, celestial mechanics is one of the most applicable parts of mathematics. The reason why it is so much applicable is that it is extremely, the n-body model, it may be some additional tricks which do not matter, is an incredibly accurate representation of the real world. it's normal in celestial mechanics to try to manipulate measurement with tiny decimal digits, significant digits, I mean, okay? So which is something which does not happen with other mathematical models. It does not even happen in all science. However, once we started comparing our mathematics with the result on space mission, we found that this was less easy than expected, as it is always the case. In particular, as reality enters in the research, it's not possible to select only the portion of reality we like. Okay, say, okay, I will consider this, but will not consider this other aspect because the model becomes less nice. Not allowed to do this. You have to use, as I like to say, consistent approximation. You cannot take into account in your model something which is small and not something which is larger. This is forbidden. As an example, and then you have to consider a lot of problems you are not accustomed to think. So let's suppose you want to study the orbital solar system body, which is normal for a celestial mechanician. But then you have also know how to measure it and from where to measure it, which means selecting the orbit of the spacecraft from which you would like to observe the body, for which you want to compute the orbit, which you want to compare with your theory. Then, from this process, which is called mission analysis, you start to discuss how big the spacecraft has to be, including the fuel needed to go there. Then we got entangled in the process of this decision to select which mission can fly. And this, of course, has to take into account its cost. Once I personally lost the innocence of pure research, there is no way back. You cannot stop and say, I will not do this anymore. Or, there is another possibility. My friend, a very good scientist, which I suppose many of you have known, did make the opposite choice. He decided never to be personally involved in a space mission. He would use the result of space mission, was never a member of a team of space mission in all his career. Now, as should be clear from what I said above, this mini course will contain a very small dose of theory, which is simply based upon my experience as consultant mostly for ESA in the design and selection of space mission to small solar system bodies. I shall explain the process of selection of space mission, at least in Europe, and some of the structural difficulties in the implementation of what was decided. I shall mention also NASA, for which I've also worked, but honestly my experience with NASA is limited, and also it occurred later than the golden age of American exploration, the one at which I assisted as a young student. While on the contrary, Colombo had the opportunity to participate successfully in that. This age was badly concluded, roughly, by the Galileo failure. Galileo mission failure, not to be confused with the Galileo system of ESA, which is successful so far. So my method in this lecture is mostly based on case studies. I shall discuss 4 or 5 space missions, small body in the solar system. I will not discuss planetary missions, although I've been involved in some of these too, both because it's not in the title of my talk, but also because planetary missions are even more complicated and they would be too difficult to explain. Now, theory. How a science mission should be designed. The theory says should always go top down. That is, you first define the goals and then find the means which are necessary to achieve them. This is the theory. Thus, what happens is that, as an example, ESA or NASA nominates a team of scientists supported by engineers, which come from the space agency and from industry, and this is normally called science team or definition team or something like that. This work starts by analyzing the state of the art of a given class of bodies: asteroids, comets, easy satellite, rocky satellite, trans-Neptunians. I'm limited to the small bodies, of course, there's same applies to the planets. And by finding which are the most relevant outstanding question, what is that is not yet known and could be important. They can be about the origin, the structure, the collision history, the composition, and dynamics of the orbit of rotation, and more. Which are the key questions? A couple of examples. If you are speaking of the moon and maybe of Mercury, the key question is about the core. Because as an example, we believe the moon has no core, and Mercury is a huge core with very complicated properties. How happens that two bodies which are quite similar in size are so much different? Or another example is, we'll see later, what is a comet? Is a comet a dirty snowball? This definition was invented in the 1940s by Fred Whipple. Or are they more like asteroids, which have a solid surface, which is not volatile? Then the question has to be, well, sexy, has to be appealing, because you always have to remember that the definition are not selected by you, but by the people who propose them, but by, in the best case, by an interdisciplinary team of scientists, including scientists which are interested in different disciplines. So it looks like a challenge. I mean, you want to find a question about asteroids which is interesting for the specialist of gas giants. Is a real challenge. The next step is to find out if existing instruments or combination of them can measure the answers. So we're asking answers, but is the answer, asking question, but is the answer accessible? And accessible with existing technology? Or if not, which new instruments have to be developed for this answer to be feasible? An important thing to take into account is that there is a big difference between the first visit to a body or to a class of bodies and a return to the same class of bodies. So the first time you see a comet, you want to know if it is a dirty snowball. The second time you go to a comet, you want to understand the physical process of sublimation from the comet and how this forms the shape of the comet and its origin. The first time you visit the moon, you want a picture of the surface to see whether there is anything else than craters. The second time you want to know about the interior, and so on. So, as an example, here I've taken two examples of first images. Just with one picture, I've solved fundamental question because it was the first picture. This is the first picture of Io from Voyager. I think there was a small one from Voyager as well. It showed Io as an orange body full of volcanoes, not an ice satellite, as it was expected. By almost everybody but one person had predicted this. It was done here. The other example is cometary, which we saw later. So the difference between the instruments for the first visit and the instruments for the revisitation, a second scientific investigation of the same body or same class of bodies, is very important. The other problem is that because of all this discussion of instruments, the science team must contain people who are familiar with the technology of the instruments. And the relationship between pure scientists and technologists is not always easy, as you can easily imagine, because the technologists want to use the instruments and is not that keen on putting the goal first. They want to use their instrument, whatever the goal. Now, the second point, which is difficult, is confronting with limited resources. But it's not enough. First of all, the study is a long process which sequences of stages. In ESA terminology, there is a feasibility study, phase A study, phase B studies, each lasting times of the order of 1 year or even more. Now, why it takes so long? Well, it takes so long because not necessary to propose only the instruments. but all the spacecraft subsystem with the necessary capabilities. You have to describe everything which is necessary to make your instruments capable of surviving, taking measurement, and sending them back to Earth. So as an example, to send a spacecraft in required orbit, it requires a budget of velocity changes. And this corresponds to a full budget, given the performance of the propulsion system and the total mass. The mass must include structure, propulsion and fuel, electric power, and heating, attitude control, communication, instruments, all the wiring. Now, one interesting thing, by speaking as a mathematician, that you have immediately perceived that this is an implicit function. That is, the mass, the fuel required depends upon the mass, and the mass includes fuel, which means this problem can be solved only by an iterative process. It's already pretty complicated. Then, in the end, you have to compute at least 4 budgets with safety margin: fuel, electrical power, data transmission, and thermostat, and budget of heat or cold. A large science mission is one of the most complex systems ever assembled. It typically requires not one, but up to half a dozen new technologies, which have to be developed specifically for the mission. Also, I have to say that often, by often, I mean in Italy, I'm being diplomatic here, this kind of global planning of a mission is not included in the formation of aerospace engineers. So there isn't any specific course at the university that says how you do this. And that is the key point. Last but not least, you need to compute how much it costs. And this turns out to be much more uncertain all the other budgets. And this, I'm not speaking specifically ESA, it's the same with NASA, the same with AIMMAIDA, anyone, Japanese, whatever. Now, is this the most important? Maybe not. But certainly Space Agency cannot undertake a mission which is going to cost more than the money they have by a big amount. The truth is, very few believe to the cost estimates. Now, the procedure to select a space mission is very complicated and colorful, especially for a science mission. At the end of each study phase, the project is presented to a large assembly of scientists and space professionals. Often a venue, in many cases in which I participated, what was used, a very large hall belonging to the United Nations in Paris, near the Eiffel. Each team is given a span of time to present a mission in a style presentation which is a strange mix of science, technological jargon, popular science, and public relations, or bullshit, actually. Each presentation is followed by an open debate. And one of the main characteristics of open debate is the blows below the belt. That is, the Republic contains all the other teams, and the only interest of the other team is to prove that you don't understand what they're doing. Okay? They try as hard they can to show that they are saying things which are stupid. And that's the difficult part. Who wins? Well, in theory, a mission scientifically appealing with a cost within the budget available and with a reasonable technological risk. If it requires too many technology which have not yet been developed, there is a risk because this technology may not be feasible in the time which is available. In practice, the cost estimate can be fake. The value of a scientific goal is appreciated different by scientists in different disciplines, and the influence of politics and industry cannot be avoided. And the main lesson I have to teach you is please learn how to lose. Be sporty, okay? Important is to participate, as the Coubertin said. As for myself, I started in the 80s by making innovative proposal to ASI, to ESA, and they didn't even listen to me. In the 90s, the first half of the 2000, I was involved in ESA studies, so part of official science team. It was in 8 mission studies for 5 different missions, 3 different ESA directorates. Well, I'm sorry to brag a little bit, but our team won in 7 out of 8 of this competition. The competition which I most deserved to win was the one I lost. That is in my own judgment. Okay. Now, if you think that once your mission has been selected, your job is done, you are crazy. It's not like that. The most difficult phase is just to begin. Due to the complexity of science-space mission and also to the nonsense of ESA budget allocation, NASA is also nonsense but in a different sense. A large science-space mission takes a decade to be implemented. The record is held by Bepi Colombo, which I contributed to design in 96-98, and at that time it was designed for a launch in 2007, arrival to Mercury in 2009. Now it is expected to be launched end of 2018, that is after I retire, and to arrive to Mercury at the end of 2025, with a total of 16 years delay with respect to the original planning.
Does it make sense? You have to redo everything, new technology, new everything.
No, because the technology did not really exist at the time the mission was selected. It had been developed in the meantime. New technology does not yet exist. With a lot of effort, we procured the technology we were expecting at the beginning. There is another problem, which is competition. We'll discuss this later. The main reason these delays are the wrong cost estimates. And the normal way of handling a wrong cost estimate is to spreading the cost on more budget years. And then the complexity of technology, which makes easy to make first order mistakes. As an example, just to take an example of Mercury, because it was a terrible example, after the selection of supplier for the Bepi Colombo bus, it was discovered that the estimate of the launch mass was 600 kilograms less than the real value. You may think that 600 kilograms is a large quantity. Engineering computation are more or less approximate, but 600 kilograms is not a good approximation, okay? And indeed, mission was continued by changing launcher without increasing the available power for ion propulsion, thus making travel time to Mercury longer than the one of the NASA mission, which had only chemical propulsion. NASA is not less subject to ESA to first order mistakes. Let me list a few of them: Apollo 13, Challenger, Contour, Galileo, IRM. Being a national agency, they are more subject to political meddling by the President and by the Congress. Sometimes, when the politics is supportive, they can implement much faster, because they have a strange decision process, but at least when something is decided, it goes ahead. So that sometimes ESA proposes a mission, like Bepi Colombo. By the time they launch it, the competing NASA mission is over. So the messenger mission to Mercury was conceived as an answer to the risk that ESA would become leader in the exploration of Mercury, and they managed to arrive there, and mission is completed before Bepi Colombo has been launched. Now let's start. So this is the end of the theory, so it's a small part. 1/4 of my presentation, no, less than 1/4 of 20 minutes. It's a small fraction, 1/8 of my total presentation. So let's start with concrete cases. So the first concrete case I will talk to you about is Rosetta. Rosetta is a mission which you have seen the results recently to a comet. The history of Rosetta begins in 1985, when an organization, a committee of ESA, which is called Solar System Working Group, proposed the Comet Sample Return Mission as one of the cornerstones of the agency's scientific program, one of the largest and most important missions. Sample return means you go there, not only make a rendezvous, but you touch the comet, grab a piece, or even pierce a hole in the comet, extract something from the inside, and then bring it back to Earth and make it pass through the atmosphere of Earth. A joint ESA-NASA study started at the end of '85. In reality, this thing was caused by the fact that it was flying at that time, a probe called Giotto, going to Comet Halley, which had the perihelion pass in 1986. And then there was a fleet of spacecraft, 2 small Japanese, 2 from the Soviet Union and 1 from ESA, which was this Giotto, flew by the comet at a flyby. That is, flyby means you pass near a body without having the capability of braking and going along with it. Because in that particular case, the Giotto probe was passing at 70 kilometers per second relative velocity, so the possibility of braking was non-existent. Nevertheless, the probe passed at 400 kilometers, less than 400 kilometers from the nucleus, and provided images. This is the image. I'm sorry, the illumination condition is not so good, but the main point, if you look at one of these pictures, maybe in a better illumination, what is this single image solved the problem, what is a comet? And the answer is more like an asteroid than like a dirty moonball. Okay? Comet has a solid crust. Most of the solid crust is refractory, which means does not allow the passage of water vapor sublimating from the interior. And then there are holes, and from the holes there are jets of dust and gas. So this was a single image. It was very expensive to make all this travel to get this image, but this image solved the first order problem. In a way, it was not possible to the others. And note that the Americans were absent because the 2 attempts to make their own, to make a early sample return and then the flyby mission were cancelled by Congress. American Congress has a possibility of intervening in NASA budget, not at the level of giving them more or less money, but each line in the budget. So they say, I spend this amount of millions for this mission. Congress will say no, or I give you half, or I give you more than you ask. Okay? This seems very strange to us, but this is the way the American political system works. Then NASA, in the meantime, decided to pursue its own comet mission with CRAF, which was a comet rendezvous, including an asteroid flyby, because comets are typically beyond the asteroid belt, so you have to cross the asteroid belt to go to the comet. While ESA and NASA together were studying the ROSETTA mission. And both were supposed to be based on the so-called universal bus, Mariner Mark II, which is roughly speaking the bus of the Cassini mission to Saturn, which also is finishing in these days, to save on development cost. Now, I have to explain to you one basic principle. Everything you buy, a computer, a cellular phone, a car, an airplane, a spacecraft, has a recurrent cost and a non-recurrent cost. Non-recurrent cost means this is what you pay the first time you do one thing like that. And the recurrent cost is the cost of each copy. So as an example, your car, the non-recurrent cost is significant, like 20%. The same is true for computers, not to speak of software. So you buy one copy of Microsoft Office, the recurrent cost is less than 1 cent. In the past, they were distributing it on a CD-ROM, and since this was costing tens of cents, they decided to get away with it, it's too expensive. And the recurrent cost is everything. The non-recurrent cost is everything. Now, in spacecraft, typically, non-recurrent cost is more than 50%. Can be 70 up to 80%, depending how complicated is the spacecraft. So, if you have to do 3 space missions, you can do the 3 of them in the same spacecraft, the total may be 80 plus 20 plus 20 will be 140%, less than the cost of 1.5 spacecraft. So, if you can design a universal spacecraft, it can do everything. A universal spacecraft for exploration of solar system, then another universal spacecraft for telecommunication, something like that. You can have enormous savings. Now, the real universal system, of course, is a myth. And indeed, the Mariner Mark II was a terrifying failure, because it was a standard, but in reality it was done for one mission. When they started looking at what had to be changed for using it for another mission, it turned out it was less expensive to design it from scratch. However, this increased the cost, and as a result, NASA first cancelled the Craft project, their mission, and Cassini barely survived until with cuts. And then also NASA entered in its worst crisis. Was due to the Challenger accident. Now, I just discovered by talking with some of my former students that they are born after that, so they cannot remember something which happened before their birth. This happened in January 1986 and was a disgusting event. That is, one big spacecraft with 7 people on board blew up in front of the and this blowing up went into the 2 TV screens, all the TV screens of the world, and repeated 100 times. So still now, you see sometimes this image, which is very strange with the kind of Y shape. Okay, the spacecraft blows up and then there are 2 rockets going one in each direction. As a result of this, of the terrible mistakes done with the shuttle program, NASA ended up by canceling most of robotic exploration missions. And then, they started having terrible failure, which the most prominent was the failure of the main antenna of the Galileo mission to Jupiter. As a consequence of this decline, NASA also cancelled the participation to Rosetta. So ESA was left alone to work on the Rosetta project and realized that the cost was exceeding the resources from the agency. Now, in practical terms, the mission was expected to cost $2.5 billion, and there was only $1 billion available. So, what do you do? Okay, then ESA, if you don't know how to solve a problem, nominate a committee. Okay? Because on the other hand, ESA wanted to do something of prestige, particularly because the failures of NASA were actually an opportunity of becoming leader in some portion of space exploration. So they nominated, they decided to make a study for a descoped, this is the jargon, descoped means that it costs less, okay? So you decrease your ambition in such a way that cost can be greatly reduced. Of course, you cannot do the same thing with 40% of the money. To be performed within the envelope of resources, that's the maximum you can spend, and now, and that then is nominated a larger team using some of the people who participated in previous and including new ones, and I was one of the new members. So I was a newcomer at a mission which had already been studied for 7 or 8 years. Moreover, I was called there as a representative of the asteroid community because I was known for my work on asteroids. So, but objectively I was less experienced than the others. Then I tried to make my job, also sustaining the interest of the asteroid community by proposing and justify scientifically an asteroid rendezvous mission, which has not been done, possibly with sample return. I proposed a compromise, visiting some asteroid which might be a comet, like something called Comet Wilson-Harrington, which was discovered in 1949 as comet and then recovered in 1979, but in 1979 was an asteroid, which is an interesting concept. That is a comet which had turned off. But still, okay, this was feasible because the cost was much more moderate, but was not considered interesting, scientifically interesting enough. Now this interesting point will come back tomorrow. At some point, mission to asteroid became very popular. But still in 1992, if you say, instead of going to a comet, you go to an asteroid, the answer was no. Doesn't matter what you say. It doesn't matter the fact that it's cheaper. In the end, the science team proposed a rendezvous with an active comet without sample return, preceded by 2 asteroid flybys. which by the way is like graph, like the proposal of NASA. The comet target was 46 Virtanen. We reached it in 2014 and the launch in 2003. Good. We proposed a big complex remote sensing instrument to be operated from a powerful orbiter, capable of operating quite far from the sun, but without nuclear power unit, which was one essential component of all the NASA mission to develop the solar system. Now this, I'm sorry, it really doesn't show very well. This is the cover of the ROSETTA this scoping committee. Okay, science team, new proposal for ROSETTA in the new configuration by ESA alone. And this was delivered in September 1993. And in principle, the mission was approved according to this proposal. I would like to show you, to be a little more concrete, I'd like to show you an example. Oh God. It doesn't show anything.
Try to scroll. Scroll down.
Sembra essere stato acquisito dallo scanner. Certo che è acquisito da uno scanner. Documents of that time were not available in digital form, so of course I had to scan the document of which I still have a copy.
Control S if you want to
No, I want to move
scroll.
to another page. Okay, let me try like this, and then. Okay, so this is, I'm showing you the structure of this document as just as an example. Okay, so you see there is state-of-the-art questions, what we want to know, then payload, with other instruments. This was more or less the scheme I was explaining you in theory. Then there is mission analysis, how to go there, how much it costs, the amount of fuel which is needed. Then spacecraft, that is the bus, what you need to have, structure, thermal design, propulsion, communication, and so on, budgets, okay? I forgot one, link budget. No, I didn't mention. Link budget means you have enough telecommunication with Earth to send back the data you have procured. That's a very essential thing, of course. You don't, this was not a first visit to a comet, so the goal was to produce an immense quantity of images and measurement from half a dozen different instruments, so you need the link budget is an essential requirement. Mission operation and management. Okay, so this is the example. Now this is, well, gives you a feeling of how poor was the graphics used at that time. These were primitive times. This is, as an example, the payload. And you already find here something, which is the fact that there is also a lander. Now, okay, I want to read you a small passage of this document, which is starting here. Can you read? Dumping, the problem is about the lander. So what is the lander? The lander is a smaller spacecraft which is released from the orbit, which essentially throws against the comet. And then the problem is that the gravity of the comet is so small that the lander can just bounce and be lost in space. Okay? So what is necessary is some form of dumping at the impact. Anyway, so otherwise the surface package got actually lost in space. In the chosen design, the surface package is still expected to rebound and come to rest as much as several hundred meters from the initial impact point. A prediction of final landing site must thus be difficult. Moreover, the final altitude cannot be guaranteed, so the design will have to cope with top-level situations. That is, what is expected that the lander arrives at the comet, bounces for hundreds of meters, not a comet as a dimension of a few kilometers, so you aim at a point and get a completely different one, and then it might end up to reverse what you expect. So you have a side of the spacecraft where you have the drills to pierce the comet, one where you have the solar cells, and then maybe the solar cells are in contact with the ground, where it's not very useful, and the drill is pointing there. So you have to do something about this. Now, this was designed of the spacecraft, very large solar panels, because it has to operate at 4 astronomical units from the sun. And now, please note this design of the lander which was proposed, which is the simplest thing, but has the capability of opening kind of legs which allow you to take a different altitude from the one which was abandoned on the surface. Okay, this is the conclusions. The in situ investigation of the cometary nucleus by surface science package has been given higher priority by the science. However, this element of the mission can only be taken into account as a PI-provided experiment. So let you decode these diplomatic phrases. The science team recommended not to have a lander because a reliable lander was certainly not possible within the resource allocated, that is the money we had. Would cost a full lander is a spacecraft. It's capable of orienting itself, maneuver, land there, push down to keep the position and not rebounding, drill to anchor to the ground, and then maybe make a hole in the surface. But this cost so much that we didn't have the money, so we recommended not to do it, rather than doing something unreliable. The agency did not accept our opinion. It said, okay, I will not take responsibility for this, but I will propose it as a PI instrument. That if somebody proposes a lander, we will transport it. But if it fails, it's not our fault. Okay? That's the way it works. Okay, this is the list of people. Okay, now let me go back to the other. Okay. Okay, this is a summary. Now, the mission about implementation. The mission was implemented, and in this case, it was not possible to say, I will delay the launch, because the date with a comet is something you cannot miss, otherwise you have to wait, I don't know, 10 years, 20 years, 30 years. However, the Rosetta was expected to be launched in 2003. I think in December 2002, the rocket launcher Ariane, which is used by ESA, had a launch failure, which lost a big satellite. And at this point, they decided to stop. The launch of Rosetta was frozen, and they launched something else less valuable in the test to guarantee that the thing would work. As a result of this, Rosetta had lost the appointment with Comet Virginia, and the mission had to be reprogrammed towards a new target called Churyumov-Gerasimenko, where it actually arrived in 2014. The lander Philae was implemented as a provided item from DLR, that is not ESA, from the German Space Agency, but it had been kept in storage, first on the ground, also because of the delay of the launch, and then in the main spacecraft for more than 12 years. Okay? Now, why is this important? Well, what happened in practice, I don't want to give you the impression that the Rosetta mission was a failure. It was a great success, but the great success was of the orbiter, of course. So I also would like to teach you how to interpret image from space missions. So as an example, this is a real image. This is, in reality, is a global view of the comet, is what is called navigation mode, something which is used to direct the spacecraft. And this shows very well that the comet is like an asteroid with one very big jet and many smaller ones. And also has this funny shape, which on the other hand is also found in asteroid, which looks like two objects, a contact binary, these two objects which are attached together. This is another thing, is a mosaic of images which is processed. This is the kind of image you find in published paper. This is not an image really, it's a composite, and then superimposed there are a lot of annotation which are used for interpretation and shows very interesting things like these strange holes, okay, which are similar to some holes which are found in the Arctic region on the Earth. Now, the third image is complete fake. Okay? So I hope you realize that the majority of the so-called images which are published by the space agency are not images. They are composite made in the same way a science fiction movie is done. That is, you take a real image, maybe, then you take an engineering model of the spacecraft, an engineering model of the lander Philae, and then put them in a position which is completely wrong, because, by the way, the Rosetta orbiter never got that close to the comet, would be dangerous, and did not go that close. It launched Philae from several kilometers. And anyway, if this was, you should ask yourself, if this is a picture, where is the photographer? Who did the picture, okay? Anyway, what happened to Philae? Philae hit the comet, exactly where it was expected, but then everything which was provided to keep it there failed. The motor did not work, the harpoons did not fire, and the reason why it did not fire is that the explosive device was expired, because it's guaranteed only for 10 years. And then performed 3 bounces, ended at about a kilometer away from the target, wedged in crevice and with the wrong attitude, which indeed did not allow neither to pierce the ground nor to charge the batteries. As a result, it worked for about 1 day and a half, the duration of the batteries, and then failed because it had no energy. Okay. Please note that during implementation phase, a lot of more complex lander were considered. There were other plans, even other names called Champollion, and all had been discarded because once it was tried to really realize them, they were all too expensive. So I'm sorry to say this, but we, I mean the science team, were 100% right. But of course, ESA managed to deny that Philae was a failure, arguing that it had transmitted some data for most of the first planned science sequence, that is the first day. It was expected to work for a month, has worked for 1 day, but they say it was a success because they succeeded in launching this thing against the comet. I mean, from a few kilometer distance, a target with several kilometers in size, this is not a very high precision launch. And then the landing site was wrong by 1 kilometer. Okay, so this is the story of Rosetta. Where am I? No, I think I'm in good shape.
Yeah.
I would appreciate if you have questions, because I don't think this is it's not like mathematics. I mean, if I give a formula, you cannot say it shouldn't be like that. But please.
One question and one comment. So, question is, you mentioned that Philae was like a packaged item from the German Space Agency.
Yes.
What's the relation between the individual national space agencies in Europe with ESA?
Okay, ESA is a confederation, is created by international treaty, which country has more than 20 members, which do not exactly coincide with the European Union, by the way. It includes Israel and Switzerland, but not include some Europe member states. ESA, the treaty regulates how ESA operates, and as it happens with European treaties, it leaves a large fraction of the power in the hands of the member states. There are always committees which contain ESA executive and the representative of the member states, and they interfere with the process continuously. So while in America the problem is the Congress, okay? In Europe the problem is these meetings of the member states. And both obtain very similar disasters, to be honest. That is, what happens is that decisions are taken, then they are reversed, and of course, when this reverse occurs, nobody consults the scientists, okay? Like the American Congress does not consult the scientists, you can imagine that this team of representatives from research government ministries and National Space Agency and the executive discuss between them, and then change every reasonable recommendation was given by the standard, just forget it. So this I have given just one example, but you can find hundreds of these. Right. And note that the science directorate of ESA is in a way the best, because at least the science director has a fixed budget, which is paid by the member state in proportion to their GDP. While the other programs are optional. Optional means ESA goes to the member state with the heart and says, put money here, please, and then I will do a beautiful mission. Okay? And then member states put 1/3 of the money which is needed for the mission, then what we do. So ESA is a very efficient working organization. And this is a typical example of malfunction of Europe. On the other hand, NASA is a national agency.
Puoi mettere un po' più in alto.
Questo qui. Like that is better? Or can you increase the volume maybe? So in conclusion, okay, I think I have answered.
Okay, and I guess my comment was just that most of the process you described about ESA does sound very similar to the process at
It's
NASA.
similar to not identical. I will comment on some of them.
I mean, I've worked on a pre-phase A portion of a proposal at NASA once, and I guess the main difference, as you mentioned, is the political meddling.
Yes, the difference is that at some point is originally the two methods were very similar. Then NASA introduced the PI missions, which is a different concept, but we mentioned this later. Okay, my second. Please.
Let's
Yes.
go back to our previous slide.
Yes.
You said that later on the Harpoon's launch device had not fired. You said that this is because of the expiry date?
To launch an harpoon, you need to have a pyrotechnic device. So it's like a gun, but something must explode. The explosion is activated by detonators. The detonators are guaranteed for a given time span.
Okay, but they knew that, didn't they?
Well, they knew that, yes, but you cannot change something when the spacecraft is already in flight. So they actually did test one detonator remained in storage, and it did not work. But at that point, what they do? Now the question you might ask is, should they have announced that Philae would fail. They didn't. They didn't announce that Philae would fail, even they knew it would fail, because they wanted to claim that it would work anyway, even if it works for a few hours. And this frankly, the attitude, I will give another example about now that will be partisan. And so the space agency has this tendency to proclaim success. And more it is a failure, more it is a failure of success that we need to survive politically with respect to their political owners. So honestly, ESA is particularly complicated, as all the European things are complicated, but I am speaking of ESA because I have more knowledge, and I think there are mostly European people here. Honestly, I cannot say that ESA is worse than the other three agencies. They all have problems. Because it is a complex problem, there is strong political pressure, and the money is never enough. And then this is a structural problem. Okay. Now, let's speak now of a lunar mission. So, I will try to cover all categories, asteroid, comets, and natural satellites of the planets of the solar system. Now, MORO, of course, well, another defect of space algebra is the tendency for acronyms. MORO is Moon Orbiting Observatory, and then MORO is an allusion to Othello, because Shakespeare, which if you read Othello, it describes the travels of Othello are an important part of the story in very desolated land. This was proposed in particular, the main person behind it was Angioletta Corradini and her husband, by the way, Enrico Costanzo, in 1993 for a selection of medium mission to be launched in 2003. The moon, this proposal, this was for a feasibility study, and then this proposal was selected for was selected for an assessment study, and so were more than 20 proposals. 7 were selected by ESA. Then a science team and an engineering team were formed, and the results were presented in Paris in 1994. So I have not written here that I actually was one of the members of this team, and again, I was not particularly experienced, in particular on the moon, but I had anyway the possibility of using my experience in satellite geology. So I proposed that MORO should release a small lunar sub-satellite orbiting about 100 kilometers distance from the main spacecraft to compute the relative range rate by Doppler effect. Now let me explain why I proposed this, because I think it's an interesting concept. You have an orbiter around the moon. Now you know that the moon always shows the same face toward us, with a small aberration, but essentially the face we can see is almost the same, apart from a small margin on the two sides. So if you have an orbiter, and this is the direction to Earth, there is a small portion of the orbit which is directly in communication with Earth. Now, if you use the Doppler effect, that is, you send a signal with a given frequency and receive it back from the spacecraft with a different frequency, and with this you measure the range rate by the physical effect, which is called the Doppler effect, then you can do this only on the portion which is visible from the Earth, because radio wave, like light, cannot curve beyond the moon. So the portion, when the spacecraft is flying over the portion of the moon which are never visible from Earth, it cannot even be tracked from Earth with radio waves. As a result, you have what could be called by mathematicians a partial boundary problem. Because instead of having a sphere around the moon, if it is a result of mathematics, maybe some of you might have heard, but if you know a gravity field of a sphere, from this you can compute the gravity field outside, and you can expand the result in spherical harmonics. You can have a very precise, if you have enough observation, knowledge. But what happens if you have information which belong to a little more than half a sphere? Actually, for an orbiter at 100 kilometers altitude from the moon, what we have is 55% of the sphere. So 55% of the area is where we can have signals. I will show you an example, because in reality, during the Apollo project, a number of orbiters were launched exactly in this configuration, a circular orbit 100 kilometers above the moon, what's called lunar orbiter, were four or five, I don't remember this spacecraft. And as a result, the gravity field in this region was well known and nothing was known on the other side. Now this is a rigorous presentation of the same thing. This is the gravity anomalies, the level curves describe the local change with respect to a smooth field, and you see very clear feature here and very strange feature here. If you don't put any a priori, you don't make any assumption, you get a very strange result, which is limited. Now this representation is, I don't know, I think it's a Mercator projection, shows the entire lunar surface, and this is the near face. And this is the error. Now the error, don't be misled, the error is small here and grows to ridiculous values. Essentially, you cannot constrain the gravity field where you have not been. Not been is not right. The satellite was there, but while it was there was no measurement. Okay? So to solve this problem, what I proposed was pretty simple. Let's make a measurement also when we are not in contact with Earth. Then if you want to make a measurement, you need 2 points. So you release a subsatellite and you measure this distance from the subsatellite. So this, I think, was a concept which is, I'm saying that I invented it, but it's a rather obvious thing to do. Okay, this would allow to measure Doppler gravity field. At that time, nothing was known of the gravity field on the far face of the moon, and nothing was understood of the global structure of the gravity field of the moon, and in particular this made it impossible to solve the problem of the lunar core, because the lunar core is something you measure by having uniform, good accuracy on the low spherical harmonics, and this is not possible if you have a half-boundary problem. The version we presented was stronger than the proposal, with the more advanced imaging spectrometer and this subsatellite. The technical challenges appeared reasonable even to ESA had no experience of lunar exploration. Indeed, in 1994, we won again. So, again, I would like to show you a document I found, which again is not only not in digital, it's not even typewritten, it's handwriting. I'm not sure how to do this. Here. Now, this was the one document distributed at the presentation in which among the 7 studies they decided to select one to pass to this next stage, which was phase A. Now, it's very difficult to read, I have to admit, but here, in my handwriting, there are the cost of each mission, okay? And this column is the total. These are the 7 missions. This is the one I was working to. There was a mission of Mercury, one to Mars, 2 experiments of relativity, one of the pure experiment of gravitational waves, microwave workaround, and star oscillations. And these were the 7 in competition. Now, the budget assigned was 345. Now the question is, who did this cost estimate and why it is in this form? They did not even distribute to us, we're listening a sheet of paper with the cost. It was just announced by voice, and I scribbled very fast on the first sheet of paper I had to get the result. So the numbers are 416, 545, 415 to 467, 404, 674, 398, 420, 448. So you first find out that all the missions exceeded budget. 2 of them exceeded budget in a ruinous way, 500, and also this mission was judged also too poor scientifically and nevertheless was too expensive. And this one, okay, Lisa. So these 2 missions were excluded because they were judged complex enough to require a larger budget mission. That is the corner. They were not right for this competition. And indeed, the result of this selection is that 5 missions were passed to the phase A, and these 2 were cancelled. This one and this one. Now this later became Colombo, was promoted to cornerstone and later was approved as a large mission with a budget of 600 million, and then it has costed a billion, of course. Okay, so the question is, who does this computation? Well, this computation are not done by scientists, not done by engineers, they are done by economists. And this economist dipende da dove sono.
Sì, perché se stai vicino a quella cassa vai in feedback con quella cassa.
Ho capito, va bene, allora sto. Okay, so the problem is you see also a number, I have no time to explain to you, all these numbers contain a lot of tricks. Some missions were presented with cost which was clearly underestimated. As an example, there are estimated. There was one mission. For one mission, there was assumed to be an American participation. For this mission, they were missing. Missing some. So there are many ways these values can be deliberately altered to obtain political result. But in general, excuse me, economy is not a science, or at least not a science with predictive value. So the way it was done is to study the history of previous missions. All previous missions had terrible cost overruns, and the result is that there is nebular values. And nevertheless, this number count a lot in the decision, because if you present to a committee says this mission costs twice what is needed, okay. So you can imagine what happened. Let me go back and tell you the end of the story.
You have 20 minutes left.
Yes, that should be enough. Should be enough. So I think I can close this.
25 minutes.
Okay. I'll show this. Okay. This was an example of image from the mission was mentioned before, a lunar orbiter. It shows something very interesting, the Mare Orientalis, which is the large impact horizon on the moon. And this was done by lunar orbiter. this shows a very nice picture which shows the south pole of the moon with an enormous Aitken crater, which is 2,000 kilometers across, which is interesting from the point of view of trying to imagine what can procure a hole like this, and also the region which is permanently shadowed from the sun and so on. Anyway, this image is not from MORO, but from the United States mission Clementine. Now, this mission had two goals. First was a technological mission done essentially by Naval Research Laboratory, not by NASA, to experiment on miniaturized payload which were necessary both for space missions and also for military missions. And then was meant to be a mission to asteroid geographers. Clementine, however, at some point during the development, they decided that Clementine, on the way to the moon, should make a stopover, on the way to geographers, should make a stopover to the moon. That is, go around the moon, not go too low, otherwise we would have difficulty in going out, and look at the moon, remain for a time of the order of 6 months around the moon, and then start rockets again and go to visit the asteroid. Okay? Now, why they did this? Because we were studying MORO, and the Americans were very upset with the idea that Europe would make a lunar mission which would be superior to the mission of the Apollo time, which is not even a great thing because it was 20 years before. Therefore, they decided to have this two-stage mission. Okay? So it was a mission with 3 different goals. Clementine was launched, made a stop over the moon, made a beautiful picture, and indeed found significant results, and then failed. Please note, this is another sign of the time. It was a software mistake. Nothing, no hardware failed. It was a mistake in the upgrade of the operating system. So just think to your computer at home and be afraid. It's something everybody is afraid when you say, do you want to update your operating system? You normally answer no. They did not answer no, and this was a terrible mistake. And then during the transfer from the moon to geographers, and then was instantly reclassified as a lunar mission. I was explaining, this is the ability of all space agencies. When they fail, they redefine success in such a way that it is success. It was a successful lunar mission, true. Actually, no. If it had been a lunar mission, it should have gone lower to the moon and then stayed there for longer. It would have been a much better lunar mission. But it was still a good lunar mission for the time being, and then failed as an asteroid mission. Anyway, it was enough to decrease the novelty of the proposed MORO investigation, and later was one of the reasons why our mission failed to be selected. Now, as I think I already mentioned, this was the mission in which I worked most personally, was most committed. As an example, I was the red book. Sorry, I forgot to show it. I want to show These are examples of. So this is the report similar to the one, actually, the one of Rosetta, which is the presentation of the mission. Now, you have to think that I was the editor of this book, so I made a lot of work. And then I was even selected as the presenter. That is one of the 2 scientists who go there in front of this huge public of enemies and present the mission, trying to show that it is more important than the others, together with another person in this large event, who was even much more experienced than me. And this was for the selection among the 5 candidates after 2 had been eliminated, as I told you. The discussion was nasty, but we managed it. And the selection was in theory decided by 2 committees, actually 3. Well, 4, but doesn't matter. That is, the missions the mission to Mars and the mission to the Moon proposed had to pass through something called Solar System Working Group, which analyzes the science missions. And then there is another thing, which is Astronomy Working Group, Fundamental Physics Working Group, analyze their own missions. Then each one of them selects one, and then there is a Supreme Committee which is called Science Advisory Committee, which decides the final outcome. This is the principle. So the two missions, the Solar System mission went to the Solar System Working Group, who selected the Mars mission, even if this Mars mission was horrendously above budget, while our mission was much more reasonable. That doesn't matter. Then the Interdisciplinary Science Advisory Committee proposed the cosmic background mission, later renamed Planck. Okay, so this is the end of the story. It's the moment to remember that we have to know how to lose. The reason why Planck won is that his executive was terribly afraid of another mission already approved, later called Herschel, and they wanted to have these two together because they knew there were synergies, and putting the two together would cost less. In the end, it cost 1.6 billion. Okay. They had an horrendous cost overrun, so horrendous that ESA was forced to cancel other missions, and it was launched 6 years late. And actually, many of the delays, including the ones of Bepi Colombo, to later program of ESA, have been produced by the horrendous mistake done by selecting Planck, maybe by the horrendous mistake done by selecting Herschel, anyway, by combination of the two. So I tend to say, when I want to be polemic, that the time I lost is the one which shows that ESA should always listen to me. Because I lost and they lost. Much more than me. So, okay, that's the point. If you have other questions, I can answer. If not, I can, let's say, begin an introductory part for what I'm going to speak tomorrow. Please.
I just wanted to mention your MORO mission sounds very similar to GRAIL.
No, well, GRAIL was more advanced because it was based on two full-size spacecraft, two identical spacecraft, okay?
Yeah.
So it was another concept. As I explained, recurrent costs are much less. So our idea was to make a big spacecraft and a small subsatellite. And NASA decided to do two identical spacecraft, but because two spacecraft do not cost twice one spacecraft, this was a good idea. But it was essentially the same concept, yes. Because they did in this case, not tracking to a full satellite, but satellite to satellite tracking. They were at a distance more or less comparable to the one they proposed, and they made the gravity field of the moon, which we have now, which is, as expected, truly superior because it's really global, and which is currently in use. Yes.
I can understand something. You said that the delay that happened with the Colombo launch was related to the other missions?
I already explained that missions are decided, but then every year they bring budget, so the mission might be approved, but then year by year ESA has to shell out the money to continue the work. Okay, if there is a previous mission which has an excess budget of 500 million euro, then you wait 1 year and a half to begin the spending for Bepi Colombo because you don't have the money to do it. Okay? So this is the problem. Having done a horrible cost overrun of more than $500 million, they were forced to delay everything by several years.
And the duration of the travel was now 7 years, but at the beginning it was designed to be 2 years. And this is just because of the...
no, this is a consequence of the change of the mass.
Just this...
The reason is, well, also the launch opportunity was not so good, but the problem was that when they discovered there were 600 kilograms more, they changed the launcher and made the spacecraft larger, launched it in space. But the ion propulsion stage was not changed. Why it was not changed? Because if not, the 600 kilograms would have become a ton or more. And that would not have been launched, not even by Ariane. So the truth is that the ion propulsion stage of Epicron was useless because it's so little power. It was supposed to push a spacecraft which is much less, and therefore it is fundamentally does not serve its purpose of getting to Mercury orbit. So, and the paradoxical result is that not only Epicron is launched many years after the Messenger mission is finished, but also if you go to Mercury, it takes more than Messenger, which did not have ion propulsion. So this is a kind of chain consequence of two big failures. One was the cost overrun version plan, and the second was the horrendous mistaking the estimate of the mass of Epicron. So it's something which is in a way difficult to believe. Space missions are so complex and their management is so difficult and subject to many constraints and pressure that it is easy in space mission to make first order failures. Failures which cost life or cost billions. Failures which are so ridiculous. I will mention later, maybe I will mention now since I have the time. Another example of failure was the mission to asteroids, which is in the list I discussed tomorrow. No, sorry, I'm wrong. It was a mission to comets. There was another NASA mission to comets, it was called COM2. It was supposed to make a rendezvous with two comets, using, of course, ion propulsion. Then, this mission was launched and was in orbit around the Earth, and then to do an additional thrust with an upper stage to get out of the gravity field of the Earth, and then we start ion propulsion. The firing of the rocket was done in a position in which there was no contact with ground control. It was done in the dark. Okay? So the spacecraft was supposed to start without the timer and start the rocket at that time. And then, when it reappeared, there was no signal. And then amateur astronomers found 4 or 5 pieces of stuff going more or less in the expected trajectory of the spacecraft. And that was the end of the story. That is, the spacecraft was blown out, and was blown out in such a condition that it's not even possible to know what happened. It's not even possible. One great thing of space mission is that you learn from failure. It was not even possible to learn from failure because the mistake had been done of doing a critical and dangerous maneuver while having no contact with Earth. Okay. You might, I don't know, maybe you don't remember these things. When there was the Apollo project, you remember how it was, maybe. The spacecraft were launched directly from Earth to an orbit going around the Moon. Then they made a rocket maneuver to circularize the orbit, and then another rocket maneuver to come back. Both were to be done on the far side of the Moon, that is without contact with Earth. But at least there were the astronauts there. Okay? If the spacecraft had literally blown up, well, that would have been a problem. But as long as there are the astronauts, and you would have known what has happened. But in the case of a robotic spacecraft, if you have no communication and the spacecraft is dead, that's the end. You are not even able to do a post-mortem. Anyway, so let me introduce only one concept from tomorrow. And the concept is, I already told you that when I proposed in 1992 that the comet mission, since the budget was decreased, should be transformed in asteroid mission, I was treated like somebody else. Okay, it was. This was never considered. Then this is the list of asteroid missions which have been done later. So look at this list. Flyby for Gaspar Edida by Galileo. Okay? Flyby to Matilda by Near. Flyby to Lutetia Stens by Rosetta. Flyby to Tracey by Chang'e 2, the Chinese probe, which was launched claiming it was the Chinese are different. Chang'e 2 was launched, they claimed it was a lunar mission, went a little bit around the moon by Clementine, and then, without this being announced, flew away from the moon and went to visit Tutatis. Okay? Then rendezvous with Eros by Near, rendezvous to Itokawa by Hayabusa, Japan, and rendezvous with Vesta and Ceres by Dawn, NASA. And this is 6 flyby for rendezvous, not to confirm failures, to the Clementine, Contour, and describe Phobos. Well, Phobos was to visit Phobos, but Phobos is an asteroid captured by Mars, so it's not counted as asteroid mission, and that failed too. And now there are 2 spacecraft now flying to rendezvous and some return. Osiris-REX. So how we did go from a situation in which an asteroid mission was anathema to a situation in which every wants to have its own asteroid mission? What has changed? Actually, we have to explain 2 things. Why the perception by the Space Agency of the importance of asteroids so much changed, and second, why the scientists are so stupid to be interested to visit a new asteroid, like so many, yes. Why the scientists continue to be interested after having seen 10 asteroids? Why you want to see more? Is there a correct scientific motivation, or this is obsession? Corporativism. I mean, I am an asteroid science, I want an asteroid mission. I don't care if it's not important. Now, this is a very important question. I will try to answer both. Okay, I have 10 minutes. If there are questions, I stop here. If not, I go ahead and say we can answer time. Please.
Do you think that the whole process of mission design could be made more efficient in the future with all this talk about smaller space missions, more lean, more?
Okay. This is a long story, both in Europe and in America. In America, there was a phase of planning a mission that was called, in which the slogan was faster, better, cheaper. Okay, so. That's ridiculous. I mean, you can make a mission faster and better, but not cheaper, or better and cheaper, but not faster, and so on. This is impossible. A mission requires resources. Yes, you can use smaller spacecraft if you do the investment in miniaturization. Both Clementine and Messenger are examples of the advantage of NASA, which has more than Europe invested in miniaturization. So you can make things cheaper, but making things cheaper is expensive. I mean, you have very high non-recurrent costs to develop very sophisticated instruments which are 1/3 of the mass, and then when you use them in the mission, you save a lot of money in the missions. But first you pay, and then you gain. You have to invest in new technology, and this new technology can pay off. You cannot just the problem is the problem of war politics. I'm sorry, people politics. The idea we have today, the politicians have today, that you want to cut to the now. So you invent a cut, whatever is being proposed by the Space Agency, and for that matter by anybody else, including elementary schools, you cut 20% because you want to spend less money. But if you do it this way, there is no way to, because you should have known years before and have had the money to invest in the technology that allows to save. If you just save, there is no strategy which allows you just to pay less for a thing which remains as good as before. This is simply not true. Certainly, this is the first problem. The second problem is that it is a matter of management and international relations. So as an example, collaboration collaboration between agencies can save money. But this collaboration is very flimsy. The only case in which the collaboration between agencies works is the space station. And the reason why it works is that they should not have done it in the first place. So, because if you ask what is the space station for, you get strange answers. And the management can be improved, but let's take the case of ESA, because we are Europeans and we understand the problem. It is obvious that ESA is mismanaged, but it's not the fault of the people there. The fault is of a treaty which does not create a clear governance system. If you have an assembly in which each representative of a single state can raise his hand and say, I want the different things and I want something for my country, the results are necessarily bad. So either you have a consistent authority which does not change every 6 months, which is, if you make a small computation of how often a government, if you have 20 European states, how often the government changes in one of them? Once per month? Something like that, okay? Well, in the United States, the governors change like that, even more. But in America, there is a single cycle of elections, which is important, even much important if you want. But we know that there is change of governance. In Europe, you never know when the politics changes. And this makes it difficult to make things in an optimal way. A colleague working at ESA, which I collaborate now, once said to me, we at ESA are not allowed to do the things in the best way. The truth is that they are constrained by treaty which says, you respect the will of the member states, because they are the ones who own ESA. Exactly the same things happen with the European community, as was known. So this is a problem we have to solve, but this is a political problem of Europe, it's not a problem of space. I'm sorry, I should not have concluded this very politically.
Are there questions?
Other questions?
You were mentioning collaborations between NASA, ESA, and other European space agencies, and saying that ISS is the only one you could think of. But what about Cassini? I've always heard that ESA and Agenzia Spaziale Italiana are both involved in that as well.
Cassini was the last of the previous era, in which NASA was doing great missions with enormous investment, billions of dollars, and ESA was participating in something smaller but still well done, and even the Italian Space Agency did something important, because they did, among other things, the telecommunication system, the antenna, and the KLM, so a number of things which are important, very important for the future. So this was a positive example, but after that, not even one collaboration between ESA and NASA has worked. I don't remember an example.
I can't think of anything after Cassini.
Yes. All things went ended up like ROSETTA, that is, we start discussing, okay, we'll discuss another case, which is called AIM. And also this, well, in this case, it was a perfect agreement, was to be a collaboration with ESA and NASA, and then both withdrew. So at least it went.
Actually, I just remembered, ExoMars was going to be NASA, ESA, but now it's ESA Roscosmos, right?
Yes.
Okay.
Because again, NASA withdrew. If you are under pressure to get results which are politically appealing for your political sponsors, the collaboration mission is not the one in which you assert a superiority. Now, the case of Cassini-Huygens was very asymmetric. So the mission, to be frank, was American, but it was an interesting advantage, an interesting contribution from Europe. To a mission to Mars, everybody understands that to get something done about Mars seriously, including possibly human exploration, it is essential to have a collaboration of all space agencies, otherwise it will never be done. Nevertheless, have you seen any motion in this direction? No, apart from the dreams of Elon Musk. In reality, there is no movement in that direction.
Okay, any more questions? Okay, so let's start our speaker.